Well, hello everyone. Thank you for coming. My name's Paul Fisher. I work for the European Space Agency, and you won't hear much from me. We're going to be giving a talk from the three scientists to my right on the role of satellites in monitoring greenhouse gases. I will pass over to my colleague Claire, then you'll hear from Harjinder, and then Emily. And then hopefully I'll have loads of questions from the interesting science that they do. So without further ado, I'll pass over to you.
Okay. Hoping my slides have loaded. Oh, brilliant. Okay, I'll stand up to talk. Can you hear me? Yeah. So I'm going to talk a little bit about a general intro of kind of how we monitor things from space, why we do that, what it is we can measure, and then I'll hand over to Harj and Emily to talk in more detail about the scientific research they do. So next slide, can I click? I can click. So this is just a short animation showing a schematic satellite orbiting the Earth. This one is in low Earth orbit. Low here is a relative term, it's about 800 kilometres above the surface. And it takes about 90 minutes to do one circuit of the Earth. So you get 14 and a half circuits in one 24-hour period. This satellite's got quite a wide field of view. That blue stripe is quite wide, and what that means is that we can see the whole Earth in one day. You can measure every point on the planet. That's not true for all satellites, it's true for this one. And that really is the strength of Earth observation, is that you can get this global picture and you can build up over time a really strong view of what is going on our planet and what is changing. So this is quite an abstract zoomed out view. We can choose any point on this planet to take a closer look. We chose Swindon. We are, I think, we had a look for it, I can't say it, approximately here, sort of southwest Swindon. I think that might be the building there. So what you can see is there's the M4 going across there. There's the Great Western Railway coming down from the northeast down to the southwest. There's a branch line that goes off. I don't know if you can see that quite so well. My absolute favourite thing on this image is the kind of curve here. Does anybody know what that is? Ridgeway. It's the Ridgeway. You can see the Ridgeway from space.
Did you want me to turn the light?
Yes, please.
Yes, please.
Oh, there we go. Brilliant. Check it out. There's the Ridgeway. Yeah, I spent far too long looking at this yesterday. So satellites don't only see what we can see with our eyes. This is from a satellite called Sentinel-2. It's designed to measure vegetation, and it can see slightly further into the red part of the spectrum than our eyes can. One of the interesting things about that is that vegetation that is growing reflects red light, and vegetation that is dead does not. And so this is what this image looks like in the near infrared. And I'll just flick between them. So anything that is bright red here is grass. It's something that is growing. And you can see, where's the laser pointer? There are some fields down here. And you can see that they show up really clearly as they're ploughed fields. There's nothing growing there. But anything that is green grassland, the whole of the Ridgeway lights up bright pink because it's grassland. And then Swindon shows up as a large grey blob in the middle of the landscape. So yeah, here's the orientation. I spent far too long looking at this yesterday. So points of interest, my favourite thing, this airfield down here, it's a disused airfield to the southwest. What you can see in the red image, the vegetation image, very clearly is that half of it is covered in grass. And the other half must be tarmac or broken concrete or something like that. The other thing I saw was this here, which shows up really clearly as a grid. And that is there's a PGL centre to the southeast. Yeah. Used to be an equestrian centre. I had to look that up. My absolute favourite thing on this image is this. Can anybody take a guess at what that is?
Water.
It's not water. That is Whitehorse Hill at Uffington, and that is the shadow cast by Whitehorse Hill onto the manger as Sentinel-2 looks forward. And it's absolutely just astonishing. And a lot of the hill forts show up really nicely here. You can just about see Uffington Castle there. Okay, so that's the local view. I'm going to show a short video now about what else we can see from space, because we're not limited only to pictures like this. So let's hope it plays. Is it going to play?
Satellites observe the Earth using a range of wavelengths on the electromagnetic spectrum, from short wavelength ultraviolet to long wavelength microwaves. Different wavelengths allow us to probe different aspects of Earth's land, atmosphere, and ocean. Light from the sun, shining at over 5,400 degrees Celsius, peaks in the visible part of the spectrum. Earth reflects sunlight, but also emits its own radiation at longer wavelengths. With a much lower average surface temperature of 15 degrees Celsius, Earth's radiation peaks in the infrared part of the spectrum. Many satellites use the reflected visible and the emitted thermal wavelengths to probe the planet's surface. The atmosphere scatters light at shorter wavelengths, sometimes making it hard to see the surface. We can often get a clearer view in the infrared. Growing vegetation strongly reflects near-infrared light. Surface temperature controls emissions in the thermal infrared. Satellites are also used to probe the atmosphere. Atmospheric gases absorb light at characteristic wavelengths. Sensors are tuned to the unique absorption patterns of different gases such as ozone, carbon dioxide, and water vapor. At longer wavelengths, water vapor blocks most of the signal from the surface, but we can still gather some information about the upper atmosphere. The atmosphere starts to clear again at microwave wavelengths. Microwaves emitted from Earth's surface tell us about soil moisture, ocean salinity, snow and ice. While some satellites tune into these emissions, others emit their own microwaves in the form of radar beams. Radar altimeters precisely measure the height of the ocean, glaciers and ice sheets. Scatterometers measure ocean roughness and wind speed. Synthetic aperture radars can take detailed images through clouds and at night, allowing us to continuously monitor vegetation, water bodies and ice flow. By sampling the electromagnetic spectrum at multiple wavelengths, we can build a more complete picture of Earth's complex climate system. With 23 climate variables and 40 years of satellite observations, ESA's Climate Change Initiative is tuning in to Earth's climate.
So the next question really is why do we measure the planet from space? And yes, it's useful for weather forecasting, it's useful to monitor croplands, but a huge part of the reason that we do this is because the temperature of the planet is changing. It's changing quite fast. This is the temperature record over about the last 60 years relative to pre-industrial times, relative to 1850. I've been working in this field about 20 years now, and the sense of urgency that it is, there needs to be action has been increasing over that time. It's redoubled this year. 2024 was the first year where we are now pretty certain that we crossed that 1.5 degree threshold in the global mean surface temperatures. It will happen again. It probably won't happen every year, but it will happen with increasing frequency, and if we carry on this trajectory, in 20 years' time, it will be happening almost every year. It will become the new normal. Today, it's a record-breaking year. 20 years' time, it's normal. So to understand how our planet is changing and to understand what we can do, we don't only need to measure temperature. We're talking today about greenhouse gases. They're the major cause of temperature change, so human-induced emissions of carbon dioxide and methane are the two biggest causes of that rise in temperature. So carbon dioxide is going up at a few parts per million per year. It's responsible for over half of the warming that we see. And methane is responsible for a further 30% or so. Now, today we're going to talk about methane mainly, and that is for two reasons. The first one is that the lifetime of methane in the atmosphere is about 10 years. It's much, much shorter than carbon dioxide. And the second thing is that molecule for molecule, the amount of heating you get from one molecule of methane is much, much larger than from one molecule of carbon dioxide. So if you can flatten this curve, if you can reduce methane emissions, it doesn't solve the global warming problem, but it buys us time. It reduces the speed of that temperature change. To know how we can act to reduce methane emissions, we first have to be able to measure them. And this is the point at which I hand over to Harj to talk about her work.
Thank you. How do I go? Okay. Hi, my name's Dr. Harjinder Sembhi. I'm a lecturer in physics and astronomy department at the University of Leicester. My research area is in Earth observation. I've been working on atmospheric science projects for about 20 years or so now. One of the particular areas of interest that my research is focusing on at the moment is on mapping methane emissions from space. So this figure here on the left-hand side, let me just make sure I do. So this just shows some of the current and upcoming missions that we have measuring and focusing on monitoring methane from space. And this little red circle is around a sensor called Tropomi, which I think that will work. Right, so this is a satellite instrument called Tropomi, which stands for the Tropospheric Monitoring Instrument, and it's on a platform called Sentinel-5P, and it was launched by ESA in 2017. Now, the whole point of this mission and the key mission objectives for Tropomi was to measure the atmospheric composition and greenhouse gases across the Earth, basically. So we get global measurements from this. And this little video here, I might be able to play it again. Yeah, so this just shows how Tropomi measures. It has quite a, what we call a swath. It measures quite wide across 2,600 kilometres, and that's about the equivalent of us sitting here in the Egg Lecture Theatre to Istanbul in Turkey. So just that's what allows us to get this global picture of how different species change over time. And the one that we're particularly interested is methane. So if I just go to the next slide. So this is what methane looks like when we try to derive its atmospheric concentrations from Tropomi measurements. So Tropomi measures spectra, as we saw in the video, and using by being able to simulate the measurements that we get from the satellite, by putting in our assumptions that we want to make, so using lots of information about the Earth's atmosphere and the Earth's system, we can then use sophisticated algorithms to try and derive the concentration of methane. So on the left-hand side here, we've got an annual average. This is just a global picture of what methane looks like. And what I really like about Tropomi is that we get global continuous measurements. And when we look at seasonal averages over time, so we would go from 2018 to 2023, we can actually see that the gradient of the concentrations is changing over time. So these continuous measurements mean that we can really start to track and see on a longer time scale how gases like methane are changing. So it's really something special about Tropomi, that we get global and continuous measurements. If we take these concentrations further and start to look daily and orbit by orbit and try to start looking at different regions on the Earth, we can then derive emissions of methane. So this is where we can start to take the concentration measurements, look at individual areas across the world. So this could be, like this plot shows, this could be some of the wetland areas and rice paddy regions in India. We've got oil and gas regions across the Middle East and America. We've got the Amazonian region. We've got hotspots across Europe, Russia, China, and we've got some in Australia here. And basically, we can start to look at what are some of the sources that are contributing to the methane concentrations that we see. And basically, we can start to figure out then and try and separate what are the natural sources of methane versus the anthropogenic sources of methane. And we know that methane can come from many different human-induced activities on Earth. So we've got the oil and gas sector. There were a couple of years ago, you would have seen there was the Nord Stream pipeline leak. We have coal mining, of course. We have dairy farming and agriculture that cause methane concentrations in the atmosphere. And we also have other things like wastewater and landfill sites. So these are all sources of methane. And the one that I'm particularly working on at the moment is on landfill sites. So how do methane emissions from the waste sector vary? So at the moment, about 60% of the global methane budget comes from anthropogenic or human-induced activities. And then out of that, about 20% of that comes from landfill and solid waste management. The rest of the anthropogenic signal comes from oil and gas, livestock, coal mining, etc. So if we were to look at the projections of how much waste we're going to produce globally, looking at 2030, 2040 and 2050 onwards, basically we're currently at about 2.1 billion tonnes of waste produced globally, and by 2050 we'll see that number is estimated to rise to about 3.7, and this is a problem that we're going to have to deal with as the global population rises. Now, one of the key things, as Claire was mentioning, if we can monitor methane, we can then sort of figure out where we need to focus our efforts and try to cut methane. Because there's a fantastic paper by Occo et al. From 2021 that says cutting methane is the single fastest, most effective opportunity to reduce climate change risks in the near term. And this means that basically, if we were to put all of our methane controlling mitigation measures that we can do now, technological measures and everything that we can throw at it now, we've got a chance of reducing the global mean rate of near-term decadal warming by 30%. So that's if we just throw everything at it now. And this is really where satellite measurements of methane come in, because we really need to be able to first track where some of these emissions are occurring in order to then figure out how to manage them and work directly with facilities and supporting them. Has anyone ever been on a landfill site? Okay, I went to my first one not too far from here a few months ago. It was quite eye-opening. I think I showered about 3 times when I got home. Possibly my research team were a little bit traumatised, but I had newfound respect for people who work on landfill sites, because at the end of the day, they're managing all the waste that we produce, right? So all of us contribute to this. But basically, how do we get methane emissions? We have waste dumped into a landfill site. So that all gathers and is poured onto the particular cells of the landfill site. And of course, as this waste sits there, we get anaerobic decomposition of waste. And what this means is that basically we start to get landfill gases produced and escaping into the atmosphere. So this is about 50% methane, 50% CO2, and then lots of other gases as well. On a managed landfill site like the ones that we have in the UK, we're quite lucky that we have these biogas capture systems. So these systems that are embedded into the landfill facilities, basically, there's lots of pipes that go in and out and around, and they try to capture some of this methane-rich gas, and it goes on to be used for renewable energy production. So that's quite good. That's quite a good thing that we've got on managed landfill sites. And then what we find on landfill sites also is that once a particular part of the landfill has been exhausted, it's been used, usually the waste gets buried and it gets sealed by different sort of permeable layers. But the problem also is that sometimes what happens over time is that some of these layerings can crack, there can be fissures, and this also then from these sort of exhausted landfill regions, you can also get methane, fugitive methane emissions escaping into the atmosphere. So I'm just going to show you basically some of the landfill sites that we've been working on. So on the left-hand side, there's this is the landfill site that I visited. So you can see basically how it's structured. I was basically standing on a hill looking down at this landfill site, and sort of behind us was this big biogas system. Because this was quite a well-managed landfill site, we didn't actually capture any methane emissions with Tropomi, so that's quite good. We did capture it with a different type of satellite, which Emily will tell you about the satellite later. We did find some lovely llama, actually, because where they've exhausted the landfill and it's been quite well managed, they tried to do some regeneration stuff, and then they keep these lovely llama on top. So that's my researcher, Dan, who made these lovely plots for me that I just showed you earlier. This is okay in managed systems, but sometimes in some parts of the world, in developing and rapidly emerging economies, we basically find that there's so much waste sometimes in some areas of the world, and you basically get landfill sites which are like huge mountains. In India, a couple of years ago, they had a huge heat wave, and unfortunately, because there was so much methane around, the landfill site was just spontaneously sort of catching on fire in different places. And this is where landfill sites become really quite dangerous. You can see you can just see how big this pile of waste is here. It's basically a mountain. And this then, for the localised area, it causes smog and lots of other nasty things going on. This is not obviously a managed landfill, it's more of a dumping ground, and you'll find that across different parts of the world you have some form of either one of these, managed sites or dumping grounds. But if we were to look at the methane emissions, what they look like from this kind of site, so this is for a landfill site in Delhi, you can see these huge plumes of methane that are captured by Tropomi, and you can see that the redder pixels are where there's higher concentrations of methane, and then you can see the yellow and the green is sort of the background. So this is what's quite special about Tropomi, that we get such a fantastic coverage on day-to-day basis that we can really start to pick out these individual plumes and try and do something about it. I'm just going to take you now to Europe. So this is where my current research has taken me. So we're working with some landfill facilities in Spain, because we actually find in Europe, Spain is quite a hotspot in terms of methane. And when we've looked at this in more detail, we find that there are these huge plumes that you can see of methane coming particularly from some landfill sites. So this is some of the work we're doing with Tropomi at the moment. So we have a project where we're working with the landfill facility, we're working with the United Nations Environment Programme, and of course we're working with ESA. And what we're trying to do is just understand what the variability is of methane across these regions. We're trying to understand what might be driving some of these emissions. Is it just coming from the waste? Is it being driven by something going on in the environment or the meteorology? But what's quite nice is with Tropomi, we're able to really track it over time, and we're able to work with the facility and try and understand what we can do about this. So where we are at the moment is we're trying to use these Tropomi measurements and embed it into some sort of methane mitigation actions. So here's Tropomi, and in this new project that we're working on, we're combining it with other satellite measurements. We're also doing some aircraft measurements, so we're really looking at this problem of landfill methane from multiple scales. And what's nice is that Tropomi gives us this regional information about methane across on a long time series. And so we're using multi-scale measurements, we're working with a ground truthing team, and ultimately what we're doing is trying to build information, actionable information that will then help guide and inform the facility operators and support them in trying to work towards monitoring, have better monitoring and working towards mitigation of landfill methane emissions. So just to conclude, Tropomi is quite a special instrument. It really gives us an overall continuous and global view of how methane is varying across different parts of the world. It allows us to track individual plumes and calculate emissions. What's quite nice is that methane mitigation is achievable by using satellite information. A lot of facilities don't really see the full scale of what their emissions might be, and this is where satellite measurements are super important. And again, acting now can really set us on a path for global mean temperature reduction. So, like for me personally, I really think now about the waste that I throw away and food waste and other things, and that's kind of nice to think that I've got a role to play in this. So I just thought I'd leave you with a couple of resources here if you wanted to understand more about the Global Methane Pledge, which is something that lots of countries are signing up to. So they're really making a commitment to try and work towards reducing methane emissions from various sectors. And also there's a link here to the United Nations Environment Programme for the International Methane Emission Observatory. Thank you very much.
Hi everyone, so kind of moving on to kind of smaller scale methane detection, but I thought I'd just kind of give a quick introduction about who I am. So I'm Emily Dowd and I'm a researcher at the University of Leeds, and my job is basically looking at satellite data and combining that with computer simulations of atmospheric methane using chemical transport models to see how it changes in the atmosphere. And on the day-to-day I spend a lot of time analysing data and using computer programming to kind of work on this problem. But I've also managed to go to lots of really cool different places and worked with a lot of different people. I've just come back from Australia, where I've been working with Australian researchers on trying to detect agricultural emissions of methane from space. I do a lot of other different things, and this project, or like this piece of work, is like looking at individual emissions of methane. And to do that, we use a satellite called GHGSat. So GHGSat is a constellation of approximately 10 small sats. And one thing that I think is quite cool about this satellite constellation is that the people who developed them named them after their children. So they're named Claire, Hugo and Iris, among a few other names. But we just call them GHGSat to make it a bit easier. And this instrument detects methane in like grid boxes of 25 meters by 25 meters, which means that you can pinpoint individual sources of methane, which is super useful. So we've already heard from Harjinder that we can detect methane from landfills, natural gas leaks, coal mines, and I think this one's quite funny. We can even detect cow burps from space. So GHGSat has managed to detect emissions from feedlots in Canada, where there are a large number of cattle being held. So one thing that's quite interesting about GHGSat is that it's not continuously monitoring. It needs to be told a target to look at before it can detect a methane emission. So I think this is where Tropomi and GHGSat can kind of work together to detect methane emissions. So we've heard that Tropomi provides daily global coverage of methane emissions, and we can pinpoint areas of large concentrations, and then we can ask GHGSat to go and look at that same area, and then we can kind of pinpoint exactly which source is causing those high emissions, so which landfill or which gas leak or coal mine. So I think that's like really, really cool. But even though that GHGSat needs to be told where to look, you can still kind of stumble across some really interesting things. And this is what happened to me in my research. So I was trying to look at landfill emissions in the UK, and I stumbled across a gas leak, which I'll just talk about now. So this gas leak was found on the 27th of March in 2023 when I was looking at a landfill near Bishop Cleeves, not too far from Cheltenham. So you can just see here, this is the landfill that I was looking at, and then we detected the gas leak just to the north of it. And this just shows a video of the plume that was being captured by the satellite data over the 2 months that we were detecting the gas leak. But unfortunately, it doesn't look like there's too many observations there, and that's because satellites that measure methane can't see through clouds, and the UK is quite a cloudy place, so we only got about 6 measurements. But whilst we were measuring it from space, I worked with another university called Royal Holloway University of London, who have this ground-based mobile laboratory, which is basically just a car with some instruments on top. And this picture up here just shows the instruments that were situated on the car, where the air is captured while the car is moving and then put into some sensors. And then we've also got this anemometer, which measures the wind speed, and then we've got some GPS. And what Royal Holloway did was they drove through the plume on a couple of different days to try and measure the methane on the ground. So they just drove along this road nearest the plume. And I think what was really interesting about this mobile survey on the ground was that when they were driving through the plume, the concentrations were off the scale in their instruments. So there was so much methane there that they were saturating their instrument, which was quite shocking to me. And I managed to join them on one of their mobile surveys, and these are some pictures that I took whilst I was there. So this picture here on the bottom shows the engineering works that were being carried out to try and fix the leak. And you can see that it's quite a tricky place to try and fix something because it's so close to a railway line. And on the other side of the railway line, there's also some other features which I kind of spotted whilst I was there. There's some areas of dead vegetation which is a sign that the vegetation was being suffocated by the amount of methane that was being released from the area. And there was also further engineering works going on down the road to try and fix this problem. So I was getting to do lots of really cool science about this, but there's a lot of work going on in the background. So I'm just going to talk you through how the timeline of events went. So we first detected it on the 27th of March in 2023, and then we confirmed that the gas leak was still ongoing on the 20th of April, and that is when GHGSat told the utility company about the leak. And then within 7 days, the utility company started their engineering works. And as I mentioned before, it's quite a tricky location to fix the leak, so it took a little while to get fixed, but they eventually fixed it on the 12th of June, which is like really great news. And we managed to confirm this with further satellite observations and also another ground-based survey. And what's really exciting about this project was it marks the first time that a gas leak has been spotted from space in the UK and then fixed. And we estimated that in the time that we were measuring the leak, the amount of methane that was emitted could have powered, the electricity use could have been powered up to 7,500 homes for a year, which is quite a significant amount. And I'm just going to point out here that it did make quite a big splash in the news when the BBC reported on it. And it was one of the most read news stories that morning, which was really nice to see that it got so much traction. And it's still being talked about in news outlets even this year. But I think one of the good things about this study is also it had really good public engagement, but it also kind of made the industry have a look at what they are doing. So the findings from this study have been used to inform regulatory change in the gas industry. So the regulatory change aims to incentivise utility companies to fix their gas leaks instead of passing on the cost to their customers. And I'm unsure if this has actually been implemented yet, but it is ongoing. But yeah, I'll just kind of finish there, but I just really wanted to say that this is a great example of how satellites can be used to reduce our human impact on climate change. And yeah, we've seen from the examples from Harjinder as well that satellites are really great at detecting methane, unplanned or not unplanned, and we can take steps to try and fix that. Thank you.
Amazing, thank you. Hello. 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 Thank you very much. Has anyone got any questions before I pipe up? Because you're the people who've been listening. I will go there, there, and there. Over to you, sir.
Hi. Just two very quick questions. The first one, how do you actually detect the methane from space? Are you looking at electromagnetic spectrum?
So something like tropomi, it makes spectral measurements. So it's a spectrometer basically, so it collects photons, we split the light, we split it into the different parts of the electromagnetic spectrum. Methane has a spectral fingerprint in the shortwave infrared. So we can generate spectral measurements, and then from that spectra, we basically then, it's quite complex, we use something called a retrieval algorithm basically. So we make assumptions about that particular measurement in time. At that time, we assume things about the atmosphere, and then we use something called an optimal estimation or an inversion method to try and infer the concentrations that are related to that particular spectral measurement in that time, because we know that that particular spectral measurement we have has a particular concentration of methane associated with it. So we kind of go a little bit backwards.
Okay, thanks. And the other quick question was, did the utility companies not know about this gas leak? And if not, why not?
Yeah, that is a very good question. I didn't have too much involvement with the utility company. GHGSat dealt with them mostly. There was complaints from residents in the area that they could smell gas, but I think the delays on trying to fix it were probably down to the fact of the location of the leak and how close it was to the railway line.
Not the place to smoke, I would imagine.
Thank you. I think a question for Emily. You mentioned about the agricultural gases that you started off talking about. Of course, they're distributed, so they don't really show up like these plumes. But I wondered if you could break down the 80% that you said of other emissions, and what you've discovered about agricultural emissions. Thank you.
So this work's still ongoing. We're using tropomi data to kind of detect agricultural emissions. But yeah, it's a more diffuse source of methane, and it's kind of mixed in with everything else, so it's very difficult to unpick. But specifically in Australia, there are large feedlots, and we're just trying to concentrate on areas and where these large emissions are. But at the moment, this work's still ongoing. So yeah, I don't really have anything else to add. Sorry.
My question was, when you showed the plots of the globe with the high concentration of methane, it looked like it was clustered, or the bulk of it was around the equator. Is there any reason for that?
So in some regions we have wetlands, natural wetlands, so they're a source of methane. We have burning sometimes and activities related to agriculture. So it's in some of these, like what Emily's saying, it's a big diffuse area, and there'll be lots of different sources sort of ongoing. So for instance, if you were to look a little bit further towards like India and Bangladesh, there's loads of natural rice paddies grow seasonally, you've got natural wetland emissions, so it all sort of mixes in basically into a massive diffuse source of methane. So you find that you've got your natural sources mixed in with your anthropogenic, and in some of the areas in Africa and across Brazil, of course, we've got anthropogenic sources as well mixed in with some of the natural sources. So things like atmospheric modelling, like some of the work that Emily's done in her PhD, it allows you to then start to separate out what's coming from natural sources and what the anthropogenic signal is from that. And that's how we try and figure out what the global methane emission rate is as well.
And is there any way of dealing with the methane in the atmosphere?
Dealing with it how? What do you mean? Well, anthropogenic, what we can all do is just try and figure out how to reduce it.
As in, when it's in the atmosphere, is there any, because we've obviously got satellites roaming around, but they're too high. Is there any way of...
obviously atmospheric chemistry, it does react with other things. So there is a source, there is a sink for methane through chemistry. Is there something else as well? I think there was...
So the lifetime of methane in the atmosphere is about 10 years. So if we stopped emitting methane completely tomorrow, in 10 years we'd have half the concentration in the atmosphere.
Doesn't it change into another...
It changes 1-to-1 for CO2, but it's about 0.5% of the CO2 concentration, so you would have some additional warming, but it's 30 or 84 times more powerful than CO2 molecule for molecule on a 20-year timescale. So the emissions really do matter, and if you can reduce how much methane you emit in 10 years, half of it is gone.
Okay, thank you.
Any more before I ask the difficult questions? Don't worry, they're not difficult. Harj, you put a graph up on there, and I think it was emissions of methane over 3 years from Madrid.
Yes.
Okay. And it seemed to peak in January.
Yeah.
Is that because of Christmas dinners being thrown away? And if not, why not?
You know what? We've been looking at this data, me and Dan, the researcher in my team, And we look at it and we think, yeah, we get it. And then we're like, no, we don't get it. It's complex. It could be that there's just so much more waste being processed through the landfill at that time. It could be related to temperature, humidity changes, the wind patterns might be different. This is what we're unpicking at the moment. So we haven't been able to find a direct cause for why it's a little bit higher in the winter, but we think it's probably a mixture of things, yeah.
Interesting graph all the same.
Yeah.
And then Claire, not letting you off. So we talked about methane, but you also were talking about carbon dioxide through the presentation. So can we look at carbon dioxide from space, and can you give me a bit of an overview about what we're doing there?
So yes, we can. We can't see quite so well the kind of emissions that Emily is talking about with the very high resolution satellites. And that is partly because the concentrations of carbon dioxide in the atmosphere are that much higher. So if you're looking for a plume, which is a small increase in carbon dioxide over what the atmospheric background is, it's much harder to see that if you've got more background. It's a little bit like if you put a little bit of red dye in some clear water, then you would see that very clearly. If you've got pink water and you put a little bit of red dye in, it's much harder to see. So there are instruments that can do it. At the moment, there's one flying and there's one in commissioning phase from GHGSat. And as of 2025, we will have 3 CO2 emissions launching, and they will be able to see at much higher spatial resolution CO2, and that will give us a much better chance of being able to see particularly global scale emissions and attributing where the CO2 is coming from when it's a concentrated source. But it's a little distance behind the methane at the moment.
And I've got one final question, unless anyone else has one other one. And this is to anybody. What can we do in the audience to reduce our emissions footprint?
I would say eat less red meat.
For methane, it's that and landfill, isn't it?
Yeah. I'm much more mindful about what I throw away. Food waste stresses me, so this is the sort of thing that's something we can collectively do. Just be a bit more mindful about what we're throwing away and better segregation and recycling.
But to be clear, CO2 is still the dominant contributor, and things like flying are the things that make the really big differences. And lobbying for change.
In landfill, can you use a different form of digestion to not emit methane and emit other gases? And are they any better or worse?
I'm not a landfill expert, I would say. But I think some of the landfills that we've worked with, so the one in Spain, for instance, they have like slightly different plants, I think, where they're transporting the gas, and they've got like digestion plants and things like that. So I think they are, they are exploring perhaps different digestion pathways to try and help mitigate some of the methane, the excess methane that's produced. So I think there is work ongoing in that, but I'm not the expert. We have an expert here, possibly.
And to our fourth member of the panel.
Just on the subject of methane from landfill sites, the government are bringing in 2 pieces of legislation over the next couple of years. One is called simpler recycling, which requires all councils to do food waste collections, and the other one is looking at a reduction in the amount of biodegradable waste going into landfill. So that should also reduce the amount of methane being generated in the UK.
Okay, that's great.
Any more for any more? Excellent. Let's make it a hard one.
Well, hard in that there's no empirical answer. Do you have hope for the future with all of this going on?
I've already been asked this twice today while we were in the main hall. Sometimes, I think, is the answer. The temperature situation is very, very scary. In methane, there are good routes to reducing emissions. In CO2, that picture is much less clear. What has changed is that I started just shy of 20 years ago, 2008, and I would regularly have people telling me that climate change was nonsense and it wasn't real and that kind of thing. That hasn't happened in 5 years. Yeah, so people take it seriously now. The sense of urgency is very real. The generation of scientists that are starting out now, they're not asking, my PhD supervisor started out asking, is climate change happening? Where is it happening? How much is happening? The generation of scientists coming through now are asking, what do we do? And it's that has been a huge shift in the last 5 or 10 years. That part of it gives me hope, but there are not clear, easy solutions anywhere in the landscape.
Well, I think it's just the more personal experience you have, I think hopefully that would motivate people to do something about it. I mean, we had heat waves. We had a heat wave here a couple of years ago. People's gardens dried up and things like that. But, 2016, I was in Delhi in a real heat wave. It was scary. So, that a couple of years ago, that was our little experience of a heat wave. Of course, we've had wildfires in the States a few weeks ago. In some parts of the world, unfortunately, I've experienced smog as well. There are things that are happening. And I think it's just when we personally experience it, it really does motivate you to try and do something about it. And I think the methane story, I think the consensus is we act rapidly now, we've really got a chance of trying to reduce even some increment of that global mean temperature. So I'm hoping we'll continue working towards that.
Yeah, just to echo what has been already said. I do think personal experience is a very interesting way to look at it, and I do think that the fact that we're getting so many new satellite instruments to try and help mitigate methane emissions is a really exciting time, and hopefully they will start to make a difference.
Thank you, panellists. Can we have a round of applause for Thank you.